So good afternoon and welcome to the fifth week of the facilitation. So I believe by now you should be familiar with the concept of magnetism that, that we started last week. So last week we were able to discuss magnetizations to the extent of defining the concept of diamagnetism and paramagnetism. So if you have any questions, you can ask me before we proceed to the next thing on our table. Also, there are some self-assessment exercises in the material that I sent to you earlier on. So, for example, in the case of what we discussed last week, you are asked to differentiate between diamagnetism and paramagnetism. And also, you are asked to list 5 materials that are diamagnetic and paramagnetic. So, if you go through the notes, you should be able to identify them one after the other. Okay, in the absence of no questions, so let's start with today's concept. Today we shall be discussing ferromagnetism. So I will try as much as possible to explain the concept of ferromagnetism, and if time permits us, we also try to look at anti-ferromagnetism as well. So in the previous sections, we have discussed and differentiated between diamagnetism and paramagnetism. Now we are to explain the concept of ferromagnetism and anti-ferromagnetism. So ferromagnetism is the basic mechanism by which certain materials, for example an ion, form permanent magnet or are attracted to magnet. So in physics, several different types of magnetism are distinguished. We have ferromagnetism, including ferrimagnetism. It is the strongest type. It is the only type that creates forces strong enough to be felt, and is responsible for the common phenomenon of magnetism encountered in everyday life. So other substances respond weakly to magnetic field with two other types of magnetism, which is the one we discussed last week, the paramagnetism and diamagnetism. But the forces are so weak that they can only be detected by sensitive instrument in a laboratory. So everyday example of ferromagnetism is a refrigerator magnet used to hold notes on the refrigerator door. You should know this. You know, when you close your fridge and you place a metal on the surface, there is a kind of an attraction towards it. So that thing that creates that attraction is as a result of ferromagnetic properties present on the surface of that material. So permanent magnet, material that can be magnetized by an external magnetic field and remain magnetized after the external field is removed, are either ferromagnetic or ferrimagnetic, as are other materials that are noticeably attracted to them. So only a few substances are ferromagnetic. The common ones are iron, nickel, and cobalt. So and most of their alloys, some compounds of rare earth metals, and a few naturally occurring minerals such as lidostone. So these are examples of ferromagnetic materials. Any question? Okay, ferromagnetism is very important in industry and modern technology, and is the basis for many electrical and electromechanical devices such as electromagnet, electric motors, you know all these, generators, transformers, and magnetic storage such as tape recorders and hard disks. So they use this concept in building most of these devices in industries, and we use them on daily basis. So we now derive the Curie-Wien law. We discussed the physical origin and properties of saturation magnetism in ferromagnetic. So the properties of ferromagnetic material of interest in technical application are closely related to the domain structure. So iron, nickel, and cobalt are known as transition elements. They and their alloys react very strongly in the magnetic field. Underline that word. In the magnetic field, they react very strongly. So they are ferromagnetic and have very high values of magnetic susceptibility. In ferromagnetic material, the mutual coupling forces between the neighboring molecular dipole moment are sufficiently stronger than the randomizing effect of thermal agitation, and the dipoles are all aligned parallel within a small region known as domain. So what you are trying to say is that ferromagnetic materials, they are very strong when you put them in the magnetic field. So also they have a very high dipole moment, and at the same time they align in one direction. If it is in positive direction they want to go, all of them will go in positive direction. If it is negative, they all go in negative direction. So now let's look at Cohen-Wend's law. Ferromagnetic material are substance that possesses a magnetic moment, even in the absence of an applied magnetic field. So the saturation magnetization, MS, is defined as the spontaneous magnetic moment per unit volume. So the Curie point, Tc, is the temperature above which the magnetic moment vanishes. So at that temperature values, the magnetic properties of the materials disappear. So if the ionic and atomic magnetic moment of a paramagnetic substance can be made to line up the same way by the addition of an interaction, then a ferromagnetic substance will be formed. This interaction is called Wend's field, or the molecular field, or the exchange field. Wend's was the first to imagine such a field. The motion of thermal agitation of the elementary particles opposes the orienting effect of the Wend's field. Perry-Wend's assumes that the Wend's field, BE, is proportional to the magnetization. So BE is equals to lambda m. So lambda in this case is the Wend's field constant, which is independent of temperature. So the susceptibility above the Curie point can be deduced from the Curie law. That is, if you combine equation 2.12 with equation 2.13, we have equation 2.14, which is m divided by me plus lambda m, which is equals to c over t. So note that we have taken the magnetic field as the sum of the applied field and the Wend's field. So you can easily see that equation 2.14 can be written as this. That is, susceptibility is equal to m, which is magnetization all over magnetic field, which at the same time can be expressed as c over t minus c lambda. This gives a non-zero magnetization for zero applied field at the Curie point expressed by this. So by the time you play around with equation 2.15, 2.16, we can have equation 2.17. All these are small algebra that you have to just take your pen and do the analysis. So equation 2.17 is called the Curie-Wend's law. This law describes the observed susceptibility variation in the paramagnetic region above the Curie point. Now let us now determine the value of the mean field constant, which is lambda in that expression. An atom with an angular momentum, quantum number J, has 2J plus I, equally spaced energy level in a magnetic field, and the magnetization is given by this, by equation 2.18, which is m ng j mu b bjx. So where x in this case is this expression, and the Brillouin function bj is given by this equation 2.14. By the time you put everything together, you can derive susceptibility, which is stated in equation 2.20. So where the effective number of Bohr magnetons is defined as this, which is equation 2.21, then by the time you put everything together, you have the Wend's field constant expressed as this in equation 2.22. So where S is the spin angular momentum quantum number. So any question on that? Okay. So now let's look at spontaneous magnetization. Here we are going to see how we can determine the spontaneous magnetization of a ferromagnetic substance. A ferromagnetic substance is said to have a spontaneous magnetic moment if it possesses a magnetic moment even in the absence of an applied magnetic field. In order to calculate the spontaneous magnetization as a function of temperature, we have to rewrite equation 2.18 so that it will give us So it will give us this equation 2.23. Then in the absence of applied magnetic field, we have equation 2.24. So please note that at the temperature T less than Tc, we obtain ms by plotting that magnetic susceptibility, magnetic spontaneous by plotting ms versus x as given in both equation 2.3 and equation 2.4. And the intersection of the two curves gives m, that is the gradient point, give us this. So any questions so far? Okay. In the absence of no questions, I think we are going to stop the class today. So please try as much as possible to go through all the classes and watch the videos so that you can keep yourself abreast of what we have been discussing in the last 5 weeks. And if you have any question, you can reach out to me via my mobile 082 60 2706 07 no 080 60 270603. That's also my WhatsApp number. Then I can discuss with you if you have any issue. So thank you for coming. So see you next week.